Okay, so let's have the next session. I am going to be leading, well not leading actually, but just participating in one session out of module 3. So module 3, as you may have remembered, that's about water technologies. Dr. Iftihar will be leading most of the session for that particular module, but I will be just doing this one part. And this is a little bit of an unusual thing to do at a water sort of workshop, so bear with me. Please. So what we're going to do here is that we're going to talk about this area of hydroinformatics. So what is hydroinformatics? This is again the use of these ICT technologies, information technologies in the water sector. So there is actually such a discipline known as hydroinformatics and something about smart infrastructure. And now we are going to look at these as water technologies. So what Iftihar Saab was mainly focusing on were sort of chemical technologies. And what you can say these are electronic technologies. So in some sense they sort of complement. That if you, for example, want to do water quality monitoring, and if you want to do data gathering, but what sort of aids are available in electronics, in information technologies to aid sort of those things. So this is going to be the outline. What we're going to do is, I'm going to once again remind you about the complexity of river basins as very complex systems of systems, why we are doing this sort of system analysis, and where does this hydroinformatics fit in that, as essentially a means to tame that complexity. Now, what these data-driven technologies of this modeling, I will basically demonstrate two sort of things. First is to do a model reduction. We will basically start with very, very complex models that maybe the hydrologists or the hydraulics experts are more sort of familiar with, but then to come up with simple things or simpler models, mainly to reason about these complex systems. And the second theme would be these information gathering devices, sensor networks. We will see a little bit of robotics as well, to essentially look at these basin scale problems at large scale. And then at the end of this presentation, what we'll do is that we'll have a little lab tour, and I'll give you a little brief on the format is going to be. So what we're going to do is that we're going to divide ourselves into 3 groups. There are 3 live demos, well, really live, but there are 3 actual demos for you. So because all of us cannot go to one place, so what we'll do is that we will divide into 3 groups. One group will go to one place, and the second to the second, third to the third, and then we will just conclude from there. So that will be, the whole activity will not be more than 60 minutes, so spending about 20 minutes at each place. Okay. Okay, now, first of all, let me just very, very quickly give you an overview of my group. So this is not WIT, this group did exist before the Water Informatics and Technology Center came into being. I call it as a laboratory for cyber-physical networks and systems, and it's a strange sort of a name for a water crowd, but nevertheless, I joined LUMS in 2008, and then since then we have been working a lot in essentially agricultural automation and robotics. So I'm essentially a roboticist by training, control engineer, and in the last 7-8 years we have been looking at a lot of water systems and hydroinformatics related issues. I just wanted to mention a few collaborations, not to sort of boast about what we have accomplished so far, but really to give you sort of feel into what sort of research are we really engaged in. So in the first row you will see institutes like EME, like WWF from ASA is just giving you a presentation. Organizations like IASA, like ICTP, the Punjab government, and so on and so forth. So we have been working with these research institutes and government institutes. On the other hand, we have also been working with academia, places like Trislotton, Georgia Tech, DLR, and other places. And we have also been engaging with the industry. So it's basically engaging the research organizations, the universities at other places, as well as these industries. And really focusing on these main 3 key themes: agricultural, robotics, water systems, and control engineering. Now, coming back to our world of water, again, let me remind you that yesterday we have been looking at essentially the geophysics and the geochemistry of what we call as a river basin. So it's a very, very complex, as we say, system of systems. So in the morning, Dr. Afin was talking about engineering systems as really the sort of ultimate in complexity of these systems. And really these river systems are a magnificent example of that. Because as mentioned, that this is not just a technical aspect. These are really very complex socio-technical systems. So on the one hand, we have this interplay of the physical elements. Okay, so this is what the hydrology component was all about. But on the other hand, there are people living in there. And we just saw in our previous presentation, when people actually interact with the basin, it's not just the technology and it's not just the science. It's really the High Court's decision and its overturning and all that. So that all of that comes into play. The institutions that are running this. So that actually makes this very, very complex system of systems really a very, very big challenge. Now, Lala, I don't know if she's here. Yesterday, by a slip of tongue, she said that, well, fortunately, we have these sort of challenges. Actually, that's not a statement very far from the truth, because fortunately for us, in the sense that, well, on the one hand, well, this is such a big nightmare to look at, because this isn't that complex system of systems. But for us, well, you can do all the merrymaking because this is really the sort of dream of a systems theorist. Because then you can do all sorts of discovery and innovation to basically look at river basins as these very, very complex machines came. Okay? And again, to just let you appreciate of the complexity. So in the previous picture, it's the surface water, it's the groundwater, these are the glaciers, the snow melt that Rasif was dealing with, and all that. And I'm now taking just one little piece out of that, just one little piece. And that little piece is the world's largest irrigation network. So again, just to remind you that just the surface water and our divergence to basically irrigate our land, that creates this very complex engineered system. And I don't need to remind this crowd of the numbers that really convey this complexity. Okay? All right. Now, again, just appreciate the complexity, and let's appreciate this complexity from the point of view of scale. Now, what we are trying to say here is that really the complexity of this basin, it comes as a problem of scale. So the technical and institutional challenges are really these problems of what sort of scales are we talking about. So first of all, these are spatial scales. So it's a very, very large net basin. So we were talking about these climate stations or rain stations in the morning, and the inability to place these stations at so many places. And I just showed you the world's largest contiguous irrigation network, and you want to monitor that. So you want to measure flows in all of these thousands of channels or outlets, and then how can you do that? So really it is the spatial scale, the inability to monitor and maintain geographically extended infrastructure. So if you go by the traditional way of doing it, this is where it is hurting us. Then there is this problem of time scales. Okay? So we want to collect information, we want to know what's going on in this system. The system is very, very complex, but it is really a multi-scale system. So there is a lot going on, and you want to collect information, and you want to react within short time spans as well. But again, the complexity of the system is not allowing you to do that. And I will actually give you a few examples of that. And also keep in mind that there is also this inability to scale the expertise. So the human scalability. So you have this, essentially the basin is our country, 200 million people. You're looking at all sorts of problems, and then if you have one federal body or one expert which is there looking at one particular problem, how do you scale that expertise to all of the variations of that problem? So the inability to scale spatially, temporally, as well as the human scale. So actually that actually poses a big problem. That you want to look at the entire basin, and then what do you do? And I think this is where this whole idea of informatics actually comes in. So let me now give a picture where I try to make this case that where do these hydroinformatics like tools they help you. So we start with our list of favorite problems, whatever they are. These may not be the biggest problems in your mind related to water, but that's beside the point. So take any problem, and then what we have been looking at in the past day or two is, well, how do we actually formulate these problems? So good science, coming from hydrology, from these data sets, looking at the geophysics, the geochemistry, and really to formulate the problem first. Okay, so and we have not talked about legal frameworks yet. The legal and economic frameworks, they actually fall into the same sort of category. So first of all, we understand the problem. Okay, and in addition to that, what hydroinformatics provides you is that it provides you a lot of gadgets, or you can say a lot of methodologies to look at those problems really to generate data. Okay? So problem formulation means that you are really, I mean, the step upstairs means that it is sort of a rational process in which you are just imagining what is possible and how things should be. And then this is where you are looking at how things are on the ground. And then the third step, which Dr. Afreen actually started to do in the morning, is where you actually bring both of them together in some sort of an integrated system analysis. So if you want to do some sort of system analysis or situation analysis of law, as you just saw there, what do you need? Well, first of all, you need to formulate the problem right. Okay? So it has to be driven by good science, by good economics, and so on and so forth. And then maybe to facilitate that process, you also need good data. And that critical step can be sort of helped by these hybrid informatics tools. And then once you do this integrated system analysis, then of course you can talk about, well, these are the sort of technology interventions, and these are the sort of other steps or policy advice or whatever that need to be taken. Okay, so this is the general picture. In some ways, it captures the essence of the school as well. I mean, these are the different aspects of the school map to these components. And this is not, by the way, not very controversial, and I think most of us agree on this. But here I'm sort of picking this step as a very special step. And I call this as a very special step because our basin is very, very different from other basins because of the scales analysis. Now, if I bring in these hydroinformatic tools, what I say is that what we are basically attaching smarts to the hydraulics in one sense. So you had this classical picture in which you were laying out these infrastructures, canals, wells, pumps, and so on and so forth. And now what we are doing is that we are bringing in a lot of electronics, a lot of measurements, a lot of interventions. And then the question that you can ask is, well, if these informatics are there, well, can they now aid the hydraulics? And this is what I'll try to make a case about. That yes, a lot can be done by marrying the. Okay. So first of all, this idea of taming complexity with simple models. Now, let me come first to open canyon growth as one example. Now, this is traditional classical sort of civil engineering, where you want to just see or you want to just model how water flows in channels, open channels, like rivers, like canals, like streams. And the traditional way of going about it is, and you can also think about some man-made infrastructures put into that stream. So you can, for example, think about gates, which are controlling the inflow and the outflow from those streams. And we call them as pools or reaches, just to sort of get our terminology right. And I put on some variables in there because later we'll be playing with those variables. So let me just spell them out. So for each of these reaches or pools, there is an in gate and then there is an out gate. So there is an upstream gate and then there is a downstream gate. This, by the way, would be actually inclined. It's not going to be flat because that is how water flows. But these steps are meant to show that this is actually inclined. And then the height of the gate, now the gates can be of different structures, but just as a cartoon, the height of the gate actually controls the opening or the head. And the head is given this symbol H. And depending on what this head is, then water will flow in. And depending on what head here is, water will flow out. And now you want to find out, well, what's going on within this pool. Because this is a very classical 101, I would say, in traditional civil engineering like that. And where they start mainly is that they would come up with these very sort of complicated distributed models, these Navier-Stokes equations, essentially done in 1D, and then they call them as Saint-Venant equations. And this is the basic structure that you go along the length of the canal or the pool or whatever, you chop it up into little pieces, and each piece is modeled by this is a little element in which you model the flow and the area as to take them as basic variables. So this Q is depending on where you are, so X, and also where in time value, so it's a function of X and T. And also, depending on this water level, there will be an area of cross section. So the area of cross section is also area X, comma T. So again, I will not go into a lot of physics and maths, but just sort of laying grounds for what's coming next. Okay. And then there are other things which are associated. I will not bother. And this is usually how you start. Okay. You basically pass these little cubes or whatever you want to call them together, and you say, well, this is a big partial differential equation, meaning it's a distributed model. You can go along the length of the canal or the length of the river to find out where exactly the flow is and the area of cross section is. And if you solve these system of partial differential equations, I will not even try to explain what these differential equations are, but just to sort of portray that these are very, very complex models. This is a distributed model, it's a nonlinear model, okay, so these cannot be solved really analytically. And if you want to know each and everything about what's going on in the canal or in the channel, you actually need to solve this equation. Okay. Now, once solved, what you will get is basically a picture like this. Okay. So at every distance along the channel and at every time where you are solving, you are basically going to get some numbers. Okay, and then you can interpret those numbers. So for example, if I make a cut at vertically like this, so this means that I'm fixing myself at 35 meters. So I'm at 35 meters at a particular canal, and I'm observing how the level of water is going up and down. So this is like a hydrograph. And if I make a cut like this, okay, so what this means is that I have frozen time. I'm looking at the entire channel and finding out what the state of the channel is. Okay, so these are basically an interpretation. So these can be both. So this is basically Q. This is velocity. What I'm portraying here is velocity. So this is one particular simulation. This is a leak simulation in which there is a breach in the canal and then water is gushing out, and that's why a lot of controls are actually sort of concentrating here. Again, I will not go into a lot of interpretation of this, but just to let you appreciate that if you want to know what's going on in a particular channel, this is what you need to do. You need to essentially solve or somehow find the flow at every distance and every time, and that's actually quite a big task for somebody to do. Okay. Now what we are going to do is that, like I said in the beginning, now if you have hundreds of channels to look at, or thousands of channels to look at, you then would be solving this for all of those channels, and then together you would want to reason with them. That, okay, there's this one particular pool that is doing this, and then that is the pool adjacent to another pool, and so on and so forth, and then this together makes a canal, and then there are dozens of canals which make up a particular canal command, and now you want to think about or reason with the whole system. So that's not the way to go, because just the numerical thinking just sort of overloads you. Now what we are proposing here is that you can actually start with very, very simple models. And I think in the morning, Dr. Asif mentioned these lump models. So these are not going to be very, very accurate models, we understand. But what they are going to allow us to do is that they are going to allow us to reason with these systems. Okay? So maybe capture the complexity at a high level somewhat. Not exactly, but somewhat, to let us think about these networks. And this is one idea, very, very simple idea. So you think about this entire pool or this reach as just one lump system. As if it's a party here, so there is water coming in and water going out. And so the rate of change of volume is really the flow coming in minus the flow going out. And then these civil engineers, they tell us, well, okay, there is a sort of an empirical relationship. Also, we saw this in the morning that there are empirical models that capture certain relationships. So the empirical model that captures the relationship between what the height of the gate is and the flow at this interface is given by this formula. So where these numbers C in and 3/2 is coming from, that is the empirical aspect. So you have to calculate. Now just plug them in here, dV by dt, and just plug them in here, and this is the model that we get. So C in is just an empirical model. The parameter for an empirical model. So this just relates that, so if I give you the height here, I raise it to the power 3/2, that's similar to the Manning's coefficient, and then you multiply it by C in. Okay, so C in is just a constant of proportionality now, but it is really a coefficient explaining how much flow is going in. It's an empirical model, it's not a physics-based model.
Here coefficient, it is multiplied by 2g and 2g.
Right. So there is an actual formula that I measured out, square root of 2gh. So thank you.
2gh and here coefficient.
Thank you.
Because it's only temporal equation, so you are facing your distance.
Good. So absolutely, that is the main point. That now we are not bothered about what is going on in the middle of the canal. So we have just picked one point, maybe the point next to this gate here. So the height here is what we are bothering about at the moment. Okay. So let me now decipher the,
Something in between the regions like outlets or canals.
right.
You can also put that.
We can also put that, yeah, as a second addition to, yeah, of course, you can do all of that. But for now, let's focus on this. Now, the only thing to note about this is that, by the way, this is dV by dt converted into dy by dt because the area of cross section is assumed to be constant. So that is why I'm replacing v by a, or that a can be absorbed into the constants as well. So this is essentially this formula which is plugged in here, except for there is this little sort of adjustment that whatever is coming in here, that is actually delayed a little bit before it actually appears here. And what does that model? Well, that actually models that if there is some water that comes in here, it actually takes a little bit of a travel time to go to the other end. So if you have, for example, your Lahore Canal, और आपके वो जल्लों के करीब आपने गेट को खोला है, so it actually takes time for that water to reach to Koga, for example. So this is that travel time. Again, engineers are very much familiar with. So really, I mean, coming from that very complex partial differential equation, what we have done is that we have really simplified it to a very, very simple ordinary differential equation, a lump parameter system, which only depends on these
We are
coefficients.
only using mass balance.
The mass balance, yeah, exactly.
Left the force balance and the
Sure, yeah. So again, I'm not at all claiming that this is explaining the physics of the problem. So we are just developing something which will let us reason about the system. Because now you can see that this is a very, very simple system. Okay, so all we need is just a delay and these two coefficients. And I will actually come back to, and in fact that is going to be our next task. Well, okay, for the Saint Venant equation, you knew how to do that because if you get the L section for the canal, meaning the canal geometry, you can now begin to do numerical simulation. But then how do you get these things? Okay, so that is the critical next step. Well, again, these hydroinformatics type technologies are going to help us. So what we are going to do is that we are going to basically start with these physical models. And again, I thank Dr. Asif for introducing this terminology in the morning, that you have these very physical sort of models. And now we are going to do these data-driven models. Because
I have to correct that. This is not a physical model, physics-based model. Physical model is something physical. You are looking like that. But it is mathematical model, but physics-based model.
okay, so I think I stand corrected at civil engineering crowd. You are talking about those scale models in Nandipur, huh?
Yeah.
Okay, I stand corrected.
Physics-based
So
model.
we electrical engineers call this as a physical model. So I think for us this is fine. But thank you for correcting that. In future I will use a physics.
Physics-based model.
Very picky. Absolutely. Okay. So from a physics-based model, we are now going into a data-driven model. Okay. And so this is really the abstract. But is it even possible? Can you really do that? And this is where we did a little bit of work. Now coming back to, again, for the electrical engineers here, and the rest can just shut their eyes for the moment. For the electrical engineers, it's very easy to see that if I just declare this h3 by 2 as one variable, this easily boils down to a linear model, which is just a delay and an integrator. Because the d by dt is just gives you the delay, and then the d by dt gives you the integrator, and then the tau just basically gives you a delay. So it's a simple integrator plus sort of a delay model. And really what you are looking at is that there is gate at the upstream and then the gate at the downstream, and this is your plant. So it's a very, very, very easily understandable model for the electrical engineers. Sorry about that. All right. Now, how do you actually now make use of these models? What are these good for? Like you said, so even though it's a physics-based model, and I thought it was a physical model, well, does it even make sense or not? And what we do is that, well, we give the system, or whatever system that we are sort of dealing with, these same sort of inputs and find out what it is doing, and then give it to the model to find out, well, what are the sort of parameters that will explain the working of the model that way. So it's a very, very, again, sort of an empirical fitting. So here what we are doing is in simulation, that at one end we are changing the gates vigorously, like closing and up and down. And on the downstream side also we are closing and opening the gates. And then we see what the water levels are like. And again, keep in mind now, this what am I plotting here? This is just the water level at one particular point. So this is a simulation maybe coming out of that partial differential equation like simulation. And then we overlay the two, and we essentially try to do a search on these parameters C in, C out, and the tau, which best explains this. So for example, the blue is the actual thing, the actual solution to the Saint Bernard equation, and red is your best fit. Okay? So again, this is, of course, is not completely reflecting what the model is looking at. I mean, just looking at them, they look similar. At least they look similar.
I have to say that red fitting and blue line is a predicted by the model, which is the mass balance equation, not a standard value equation.
So the blue one is the Saint Bernard equation.
You are solving this equation. This is not a standard value equation.
What I'm saying is, okay, wait. What I'm saying is that I have solved the Saint Bernard equation. And then after solving the Saint Bernard equation, I have taken just one cut at a particular distance, okay? And that is the blue line. Okay? Now I take this model, and it is now composed of these three parameters, and I search for the three values of C in, C out, and tau that somehow align with this, and that is actually the red one. Okay? Right? And by the way, this is all in simulation so far, and then you can find out what the parameters are. We actually did this in actual. Okay? So just to see whether this works or not. Okay. So these were some of the experiments that we did at, so this is a channel known as Cara Distributory. I don't know how many of you know about this. So this is just right next to, so it emerges from Jallo, where the Lahore Canal emerges, and then it comes all the way here to Laos. So this is an old distributory which is no longer used for irrigation purposes. So we had permission from the irrigation department. This is really our test bed for the last few years where we have been doing these things. Okay, and what we did was that the procedure was that we actually placed these water level sensors at the point where we wanted to do this, or to verify this sort of model. And then we just opened and closed the gates to find out, well, whether our models were fitting or not. And let me actually play a little video. I will skip the map. This is just a little bit of detail about, well, what did you need to do? This is just a discretization of the model and just the playing with the gate structure. Now I'll play a little video just to, I don't know, maybe it will not excite the civil engineers, but at least it will excite the non-engineers. Okay, so this is a release, and I think the irrigation people allowed us to do that, and all of a sudden you pull the gate, and then this water is gushing through. So this is the travel that I was talking about. So this is an actual experiment, just to let you know that we did actual experiment. And I think the irrigation people, they don't allow to do these sort of things in normal canals. Okay, so this is what we call it as a step test. Okay? So you all of a sudden you open the thing, and then you do the step test. So very electrical engineering like thing. And then so these are the responses. Okay, so you give the step, and then these are the different recordings of water levels at different places, and then you go back to your algorithms or to your search method, whatever you want to call it, in order to find out, well, what is the model? What are those three parameters that best explain it? So a few things are very, very easy to find. So for example, the delay, so you give it the start, and then of course you wait, and you wait, and then when the water level starts to rise, you just note the time between these two incidents, and that is your lag. Okay? And then from these curves, now these are again very familiar, those RC-like curves, those first order curves that again system status are very, very familiar. Okay, and from these you can extract these parameters. So by the way, this was work done by some of our students in a final year project, actually multiple final year projects. And then you overlay with the model to find out whether the model was making sense or not. So for example, this is the actual recorded data, and of course this is what the model is saying. And of course they are not agreeing that much. But really the power that we now have is that now this very, very simple simulation, and again those who do modeling will appreciate that this very simple model is much, much simpler than that partial differential equation. And if you now want to play with dozens of channels or hundreds of channels to see what is going on, I think now you can begin to reason with them. Okay. And we also went further and played with this idea of downstream control. Now, downstream control in our system does not make a lot of sense because we don't have we don't have storage in the system. Okay. So I don't know how many of you know about difference between supply-driven and demand-driven irrigation or supplies. Okay, let me make an analogy. So first, करें आपके पास पानी है. So you are in your house and you have water coming in, and the water comes in 8 a.m. in the morning and goes out at 9 a.m. तो अगर आपको पानी चाहिए तो आपको उसी वक्त जाके आपको भरना है. Okay, so that's a very supply-driven sort of thing. That you are given a schedule, and this is the only time that you have water available, and this is the only time that water can be used. Now, and the water is just rushing in. There is no the tap; it's not there. So imagine that the tap is not there. Now, if you can, I can provide you with a tap. So the tap, what actually gives you is the ability that जब भी आपको पानी की ज़रूरत हो, you would open that tap, and then you will be able to use that water. Okay? And what enables that is not only just a tap, but actually some reservoir behind it. Okay? Now the idea that we played with was that in these canal systems, what we have currently is a very, very supply-driven system, in which via these ideas of Varabandi, what they do is that they basically flood the channels, they give out a certain schedule, and then they flood the channels, give a schedule, इस हफ्ते इसको पानी मिलेगा, इस हफ्ते इसको पानी मिलेगा, इस हफ्ते इसको पानी मिलेगा, okay? And that's because we don't have any storage. Now what we sort of played with was, and what the Australians, for example, have done, and the Europeans have done, that you can actually convert these canals into these tap-like driven systems. इसमें आप क्या करते हैं कि whenever you want water, the farmer actually places order. So you can go to your smartphone and say, well, आज मुझे सुबह 8 बजे पानी चाहिए, and then the irrigation department will make sure that water reaches your. So that's a very fancy idea for, but nevertheless we can play with that. So for that, we sort of played with this whole thing, and we actually implemented this thing on Paradistributed tree, where, so this is the irrigation channel that we have just begun to play with. We have these simplified models, and then using control kinetic techniques, we came up with controllers and then some gate automation stuff, and which probably you will see in the lab, and also water level sensors, which also you will see in the lab. Okay, so now we have the ability to measure water level. We have the ability to move the gates up and down, and via that you control, or you basically convert your channel into this tap-like thing, where whenever you want to open it, you can open it. Okay. So these are just some pictures from that student group that built that thing. So I have a short video, but I think I'll skip that in the interest of time because I have more things to show you. Okay, these are again a more advanced implementations of this idea. So this is not, of course, Pakistan, where people have actually implemented this. So this is an Australian example where these are the sort of controlled gates. You can see that there are these solar panels there. That means that there are a lot of smarts built into these gate controllers, where there is an ability to receive commands and to receive measurements and then open and close the gate somehow, and some intelligence also sitting here to make those sort of decisions. This is relatively more primitive, but nevertheless, this is also in operation. Okay. So there are examples in Australia, in Europe, in USA, and in China. All right. Okay. So how does this basically work? So let me just show. I mean, this is cute to look at. So for example, this demand-based supply system. Just assume that initially, so this is your channel and these are your reaches, and your entire channel is empty at the moment. Okay. So this means that if you, for example, you want to fill this up with a certain amount of water, there is demand here. So this is where the gate gets activated, and you try to fill it up. So now, because there is no water back here, it will issue the command one step back, and it will open this gate as well. Now, this is also empty. It will generate another command back here, and then this gate will be open until you get water. And then assume that this is where you start to fill up. Now, when you get this, then so all of the gates are open. Now you start to fill in. Okay. Now it's filling up, and up and up and up. And now here the water level has been met. And now the gate command has been given to shut down this gate because this is now closed down. But this is still filling up and up and up. Okay, so this is a very simple idea of how do you actually start with these. And now what happens is that, for example, in the very last pool, somebody, farmer, for example, starts to take up water. And what will that do? That will lower the amount of water in the last pool. So let's simulate that. Oh, basically it's simulating it here. So this particular pool has, there was an off-take here, and they have consumed water. And because you needed to maintain balance here, what happened? Okay. So it issues a command to open up this gate, and from here water will come up here. But if water comes up here, then there is shortage here. Okay. So this shortage actually just travels back and back and back until you can actually go back to your original situation. Okay. So this is the idea of that demand-driven sort of delivery. So instead of just flooding the channel sort of blindly, what you are doing is that you are generating demand and then you are acting to mitigate your losses. Right. So you can play with all sorts of things because now you have the capability to do that because of this sort of automation. So you have the capability to measure and you have the capability to intervene as well. Okay. It's a smart water grid. But really, technologically that is possible. But then you also want to verify, well, does it even work? I mean, now you have all of these tools linked together, how does the performance is like? And I think this is where these models that I just mentioned to you about, these actually come in. And now what you can do is that you can play with these, series of boxes and boxes, each boxes basically depicting those models that we have just discovered. And these models are interacting with each other, and then how do these interact with each other to generate a certain demand, to fulfill a certain demand? You can play with that. People have actually done that. So you can play with architectures. This is just a bare system. What you can think about is that, well, what if each system or each subsystem has its own controller? That is one way of controlling it. Or you can transmit all of the information in the center, or you can have some sort of a mixed architecture in which the gates are talking to each other or talking to their neighbors and so on and so forth. Again, the reason that I'm showing you this is that now you can actually think about all of this. So it's a complex system, of course. If you wanted to do this with those original physics-based models, this was not possible. But now with these sort of very simplified sort of models, you can play with that sort of complexity and think about architectures, control performance, and so on. Okay, so this is that centralized sort of control. Right, so for one channel. So it's possible for one channel. So this is what I'm saying. For one channel you can do that, but for 20 channels, like for example, we did a certain automation in the Akra Canal branch in Bhavanagar, and it was an 18 canal distributory system. So 18 is a significant number. So if you want to solve 18 solvers at once and do measurements every 10 minutes or 1 minute, it becomes a very, very complicated thing. So this is again managing complexity. Yeah, but you can do that for supply-based systems. It's a very difficult, but so this is the beginning of the idea. What you can do is, and what people have done is that you can actually mix the two. You can mix supply-driven and demand-driven as well. So the schedules you can optimize midway and reissue schedules. Although that is not possible here, because there is a legal barrier to that. Because आपके जो legal right है, you cannot override that. So अगर आपको बारिश हो गई और आपको पानी मिल गया है something, you would still get the water. So that is your legal right. So that actually connects to the legal part of things. Okay, so now we are outlining a technology that can be implemented. Lekin the legal framework is not allowing you to do that. So that is why it is important to understand that aspect as well. Okay, now just as a final this is a final example of what you can do with these systems. Okay, you can also talk about or think about, well, how do people behave with these systems? Okay? And behave with these systems in an analytical way. So, for example, suppose you have this box that represents that canal model that we just discussed. It can be that very complicated thing or that simplified thing. And now you have this controller. And now it is talking to these communication networks in which commands are going in and coming out. And then somebody tampers with it. Somebody injects something inside. Now this communication network, by the way, is just an abstraction. It can be just a manual operation. उस मैनुअल ऑपरेशन के अंदर भी आप सोच सकते हैं कि क्या पॉसिबल है. Now what I'm again outlining here is that, well, if you try to tamper with gauge readings and if you try to tamper with gate operation, क्योंकि उसके लिए इतनी advanced technology की जरूरत है, you can do that for the manual system as well. You can now begin to analyze that in this framework. Again, this was not possible in the previous sort of very hydraulics intensive framework. So I will again not go into details, but it just tells you that there are ways to go about it. And then there is this particular simulation in which, for example, you have these beaches. This is that system, and if you do things in a certain way, it is able to. I can show you how to steal water from this system without the gauges able to know that what has gone wrong. Okay. Again, so I'm explaining to you how water theft has taken place in this system using analytical methods. You can say that these are all ideas coming from systems theory, from these analytical tools that you can now. And again, this is possible because you have simplified models, not these very complex models. Okay. Now, and then what we are talking about here is a very complex, what I call as a network smart water grid. So there are a few sort of terms to throw out here. Those of you who are interested, there is this whole idea of Internet of Things or cyber-physical systems, and this falls into this. So the cyber elements are the rivers, the water courses, the barrages, the waves, and the cyber elements are sensors, controllers, communication, and so on. Okay. So let me just outline once again. Those of you who had enough with the analytics, just the take home, that if you equip your system with all of these electronic gadgets and these modeling techniques, well, at least you can think about what's possible. First of all, you can think about ways to increase efficiency, because now you are monitoring systems. So this is very much clear. You can talk about demand-based delivery, which we just played with, or maybe a mix of demand and supply-based systems. You can also talk about control of non-technical losses. Thefts is a very sort of a fancy name for thefts. So I just showed you how to at least analyze analytically water thefts. Unauthorized dump, somebody is dumping something into your channel, and then you can analyze it. So general system has monitoring, flood breach security, enforcement of water rights. I think this is very important. Okay? So your legal frameworks, they give you that आपको इतना पानी मिलना चाहिए. Well, somebody has to somehow make sure that आपको ये चीज़ मिलेगी कि नहीं मिलेगी. Okay. Now this takes care of the first part in the sense that I initially talked about river basin complexity, and I said कि देखें इतने complex system को आप उस directly physics-based models के जरिए जो है वो शायद you cannot even begin to understand that, and you need to come down a little bit and talk about simple models. Now what we are going to do next is that we are going to think about information gathering. Just a very complex system, और उसके अंदर हम चीज़ों की बारे में information जो है वो कैसे collect कर सकते हैं. And I'm going to give you a little glimpse of what are the sort of technologies which are available by which we can gather information. And this will be our lab tour, where we will basically view 3 technologies. So one is just measuring flows in irrigation canals. Okay. Second technology will be measuring flows in small outlets. मोगास कह रहे हैं हमारे जो छोटे drains हैं, उसके अंदर आप कैसे उसको measure कर सकते हैं. And the third would be a measurement of siltation, sedimentation in the canals using these aerial drones. Okay. So we will show you some fancy robots in the meanwhile. Okay, so just to give you an overall picture, so this is our first demonstration. This was a project that we did in 2012-2014, in which we instrumented a full distributory irrigation canal system in Bhavanagar, where we installed these sort of ultrasonic sensors to measure flow in a particular irrigation canal. This is a telemetry, telemetry system. So we did that. So this is a spinning well that we built. We will show you a mock of this built-in NUMS campus outside. You do that. The measurements are made by this wireless sensor node. It basically takes these measurements, sends to a server where this information is displayed to the public. Okay, it's a very simple sort of idea. Okay. The second technology that I'm going to show you are basically these aerial drones. Okay. So what is this all about? Well, you have heard the word calcified. Okay. So every year the canals are forced. to essentially find out कि कहाँ पर जो है वो sedimentation हो गई है, वैसे ही cleaning की canal को ज़रूरत है, and if you all of you must know that this only happens for 2 to 3 weeks in a year जब वो the canal closure और उसमें ये करने की कोशिश करते हैं. The idea here is basically automate that process. So we are not going to do a full automation of the cleaning itself, because that is actually too much of an automation for us, even for us to think about. But what we are going to do is that we are going to basically see how do we actually automate just the surveying process. Okay. So we need to first of all find out the sedimentation we can use. And the idea is that you can actually use these newly available sort of drones. And what we have done is that we have modified some drones to carry these instruments. These are these measurement devices, so-called laser scanners and cameras, which can go along the length of the canal. And the idea is to make them go along the length of the canal autonomously by themselves, because these are long stretches. And during that, they will try to measure these sort of channel degradation. So taking channel cross sections and trying to measure from how things were in the last year. So I will just play a little video, because we don't have the drone flying right now, just to sort of again show you that we have something which is working. So this is the channel which is in the campus on which this drone is flying. It's carrying its instruments. Okay, so this is going along the length of the channel, and meanwhile it is carrying some sensors which is taking its cross section. I think when you will visit the lab, you will see more elaborate measurements and what it is getting. Okay. So these are just some technical detail of what is going on. We will go into the lab and see what's going on. Okay. Now, why was I showing all of these three things last? So remember my initial slide when I said that there is this problem of scales. Okay. So there is this inability to monitor these infrastructures which are very, very large, geographically very, very large, and then the ability to take measurements at very short intervals, and then the ability to expertise human scale. Now let me actually reiterate. What have we done in these 2 or 3 examples that you're going to see? Just see. So where does the geographical scale come in? So how do we take measurements on these canals at the moment? बता सकते हैं? How does the irrigation department collect data for daily flows? ठीक है, so gauge reader है, वो सुबह 8 बजे जाता है, जाके पानी का लेवल देखता है और उसके बाद वो रिपोर्ट कर देता है, ठीक है. So you have thousands of channels now. People are going there 8 a.m. up in the morning and they are making these measurements. And now what is the first example? What does that do? It is basically essentially automating that last part in which the gauge reader no longer has to go there. You can do that as many times as you want in the day, ठीक है. Or you can actually take those measurements at as many channels as you want, ठीक है. So that is the scaling part. इसके अंदर आपको वो जो आपका manual operation है, you have essentially done that. What about the second part that we have that I've showed you? This drone example. How does the complexity or the scaling complexity कैसे manage हुई? Anyone? So let's talk about geographical scale. So what do these drones? How do these drones help us? Right. So I mean, previously, how were you doing it? Manual measurements thing, and if you close the channel for 3 weeks every year, and if you have thousands and thousands of kilometers of channels, is it possible to do? It's not possible to do it. So that very large system, उसकी mapping क्या है, उसकी measurement क्या है, that is being done. And what about time? Time scales के अंदर कैसे help कर रही है? Again, that time constraint that we have covers more. और वो जो पहले वाली एग्जांपल थी गेज रीडिंग वाली, उसमें हाउ आर वी कवरिंग टाइम? सो रिमेंबर दैट दोस मेजरमेंट्स वर एवरी 10 मिनट्स. Okay, so that's actually transparency वाला जो मामला है, वो तो बिल्कुल यानी वो that problem is on top of all this. अभी तो हम सिर्फ बात कर रहे हैं कि सिर्फ information gathering की, तो even if we wanted to do a 10-minute measurement with the current system, the current Pansal Luis wala बेलदारी वाला system है, is it possible? I think it's impossible. Even if you deploy 1,000 people at every point, हर 10 मिनट के बाद कैसे आप measurements ले सकते हैं? Exactly. So वो तो आप कर देंगे, यानी कि आप कहेंगे तो वो कर भी देंगे. And the last thing, what about human scale? Human expertise, कैसे हमने scale की है using these things? Okay, so one thing was transparency. So वो हम ले आए और precision और So one idea is very clear. देखिए अभी इधर से जो data आ रहा है हमारे पास, that is just the tip of the iceberg. Because that data, whatever that you are measuring, and I think you will probably see glimpses of this. So these are some of the recordings that we had from that canal telemetry system. Now, once you start to record this data, you don't just stop here. Then you begin to analyze it. And once you begin to analyze it, then you say, oh, the irrigation वाले तो ये कहते थे कि they have this irrigation roster where you are supposed to open and close the canal. This, by the way, is year-long data for these canals. Or you can see that sometimes the canal is shut off and sometimes the canal is. And the labeling that we have used here, these reds and blues and greens, what they depict is that whenever there is a red, it means that the canal was supposed to be shut down. Okay. Well, we did not find many of those cases. So actually, they were very clever people. So कम से कम जो बावल नगर में लोग हैं, वो अपना काम अपनी वो हाल तक आ रहे हैं. So they are maintaining the schedules very well. I mean, you can actually detect that. So that schedule, whether it is being kept or not kept, I think this can be. What else? Well, if these are flows, and if you now start to do area under the curve, what do you get? The volume. Okay. And then you divide it by the canal command area. Now you can actually play with equity. हर एक को उसके हिस्से का पानी मिल रहा है कि नहीं मिल रहा? So that's the systems analysis. This is where the systems analysis now starts to kick in. Now, once you start to gather this data, it helps you to scale that expertise in the sense that whatever decision making that previously only a high-level official in the irrigation department was or could have done. Now, this I think a simple farmer can also do if you provide him or her with a little gadget or a little app or whatever to find out कि आपको उसके हिस्से का पानी मिल रहा है. This is really the scaling of expertise. Okay, so what I've just demonstrated here in all of these examples, and let me just come back. First of all, these are the take-home messages. I understand this is an unusual talk for a water sort of workshop, but if you just remember this is fine. First of all, I've again tried to make this case that these river basins, these are extremely complex systems. They're extremely complex systems, and these require this sort of integrated system analysis like approaches, and this is not possible without data. As you've seen this again and again and again during this course. And data-driven modeling is really the key to such studies, which requires smart infrastructure. So when we say about smart, then we need to make some gadgets or some things. And these complexities, I've shown you that they can be tackled using two ways. So one is actually making some things, these electronic instruments and gadgets and robots, and also thinking abstractly. Sort of graduating, or in fact descending actually in some sense. Coming down from these very exact physics-based models to sort of these very more informal but really data-driven models. And they actually let you to think about these systems in a more sort of systematic way. Okay, so this is where I will stop with this presentation. If there are any questions I can take, and then we can go for the lab tour. Right. So people can play with that, yeah? Sure. So not only that these are not accurate, we are fully aware of that. Not only that these are not accurate, but we just talked about sedimentation. As the channel gets tilted, this will actually get, they will change during the time of the year as well. So given that all of these things are there, but would you now prefer to play with that model, or again there are those same Bernard equations, which are prone to even more of those problems? So the channel geometry, अगर उसके लिए change हो रही है, तो उसके लिए सबसे भी ज़्यादा change So that again that can be incorporated. But then you are actually just chopping it down into smaller parts. But that is just a second order sort of.
So currently in our irrigation system, yes, we right stuff, everything is lined up.
No, by the way, nothing is. I have a. Yeah. Sure. So I have a lot of respect for the irrigation people, by the way, अगर हैं यहाँ पर कोई लोग. I do not have a lot of respect for some other departments जिनका मैं नाम ले लूँगा, but I have a lot of respect for the irrigation people क्योंकि वो जो कर रहे हैं वो ठीक कर रहे हैं. उसकी वजह ये है, but they really need to scale up. Scale की बात की. Reason I'm saying this is, for example, this 8 AM measurement that the baildar takes every day. जैसे वो कह रही थी पता नहीं वो ठीक है कि नहीं है, जब ये साहब से यहाँ पर उसको dispute कर रहे थे. Whatever that is being put up every day for the last 10 years and never make it. All of that is there. So Punjab government is doing a fantastic job with that sort of transparency. The irrigation schedules, जो बाराबंदी के schedules हमने बात की थी, they are available. That's a different department. Yeah. Okay, so should we start the lab tour now?